Hello, complex students. So we have a little bit more to talk about with contour integrals, establishing a few theorems and sort of boundary cases. So we'll start with the boundary case. So the issue that we want to look at here is, what if the contour of our integral sort of passes over some discontinuity in the function? For example, S might happen at a branch cut for the function. Maybe we can relate to something that we've seen previously in calculus. You may remember the idea of improper integrals. So improper integrals are where the function is not continuous on the interval in question. So for example, when we look at this integral from 0 to 1 of 1 over square root of x, we see that 1 over square root of x is not defined at 0. So it's discontinuous there. In fact, it has like a vertical asymptote there. But it turns out that you can give meaning to that integral even at a place where there's an asymptote. You just have to figure out how to handle that endpoint. The way that you would give some meaning to this integral is you would you'd take the limit as, let's say, t goes to 0 from the right of the integral from t to 1 of 1 over square root of x. And the integral that you see here in this expression is perfectly fine because t is greater than 0, and so the function is continuous on that interval, and the theory says that the integral exists. So, and then you can evaluate that integral in sort of the standard way before you take the limit by getting an antiderivative, which would be 2 squared of x, and evaluating that from t to 1. And then what does that work out to? Let's see. Limits t goes to 0. Plug in 1, you get 2. You get minus 2 square root of t. And then as t tends to 0, the square root of t term goes to 0, so you just end up with 2. So we're not going to do integrals exactly like this, like replacing one of the limits of integration with a variable and then taking a limit. But it'll be a little similar in that we'll need to make the function that we're trying to integrate continuous on the domain that we're trying to integrate. In the picture that you see here, I'm depicting the function has a branch cut, that dotted line, and then the contour over which we're integrating passes through that branch cut. So what do you do in that sort of situation? What it comes down to is that the definition of contour integral here in yellow, so for the contour, you have to have some parametrization of the curve, and you essentially just substitute in place of z what the parametrization of the curve is into the integral, and then use the limits of integration that are just the limits of the parameter for the parametrization. That gives you a new integrand, and if you can make that integrand continuous on a to b, then you can integrate it. So it might be that at this one point where it crosses the branch cut, the function's not defined there. So the idea is you'll have to give the function some definition there just at that one point in such a way that it makes the integrand continuous, and then you can integrate it using normal means. So let me give you an example of what I'm talking about here. So in this example, we want to integrate the square root of z over the contour, which is a radius 3 semicircle centered at the origin, going from 0 to pi. So you can see the picture on the right there. And you can see that the right-hand endpoint of that curve lies on the branch cut that we're going to use for the square root function. So the point here is that the integrand of the function, the thing that you're integrating, is just not defined there. And so we have to give the function some definition there before we can get away with doing the integral. So let's see how this would work. So if we started trying to do the integral over c of z to the 1/2, where we're choosing this specific branch of the square root function, and we have this specific parametrization, then okay, we substitute in the parametrization, so z, so we're doing 3e to the it to the 1/2. Then we have to multiply that times z prime, so that's 3i e to the it. Then we got dt, and the parameter runs from 0 to pi. And let's simplify that a bit. How do we do that 3e to the it all raised to the 1/2, we have to look at this definition up here in yellow. And so this will be integral 0 to pi. So we've got to do log of z, where z is this 3e to the it. And so remember, when you do log z is natural log of the modulus of z plus I arg z, right? Where we pick, in this case, our arg is going to fall between 0 and 2 pi, endpoints not inclusive. So because we've got the number there inside the 1/2 power in exponential form, we can see what its modulus is, and we can see what its argument is. Its argument is t. So this ends up being e to the 1/2 times natural log of 3 plus, and then the arg is just it. I mean, I times arg is just I times t. And then that's still multiplied times 3i e to the it dt. So what we have to worry about is giving this function that we're trying to integrate some definition at the angle t equals 0, where it's not defined at this point. Let's simplify it a bit first, so that e to the 1/2 times natural log of 3 just ends up being square root of 3. And then you've got e to the 1/2 it. It's going to be multiplied times e to the just it, so that there you'll have, also have an I here. There's a, yeah, so we'll have 3 square root of 3, then there's an I. Those are your constant terms that are remaining. And then you end up with e to the 3it over 2, just from adding the exponents of the exponential terms with the variable exponents. So let's just note that the expression that we have on hand here, you could plug t equals 0 into it, and we could get a value that's compatible with what we're trying to do. So let's define, the original thing that we were integrating was this z of t to the 1/2 times z prime of t at t equals 0. Let's just define it to be what we get when we plug 0 into the expression that's currently in the integrand above. And if you plug t equals 0 into that, you get 3 square root of 3 times I. So that makes that function continuous, because we're making the expression equal to what you get when you take the limit of it as t equals to 0. This makes that expression z of t to the 1/2 times z prime of t continuous on the entire interval 0 to pi, so we can integrate. And so carrying on with our integration then, I see that I could just do an antiderivative of that expression that's inside the integrand. And what do you get? Well, you're going to have to divide by 3/2 I, so the i's are going to cancel, the 3's going to cancel. It looks like you end up with 2 square root of 3 e to the 3it over 2 evaluated from 0 to pi. And then when you plug in pi, you're going to get e to the 3 pi over 2, 3 pi I over 2, which that just comes out to negative I. So you'd get 2 square root of 3 times negative I minus, when you plug in 0, you get 1. So there. In some ways, the problem that we were encountering was kind of transparent in this particular thing, because if you hadn't even thought to consider that, the function's not technically defined there where t is equal to 0, it would seem to be defined just because of the expression that you get after you simplify the integrand. But technically it's not, because we're taking the 1/2 power at that point, which is on the branch cut. So we had to say, hey, function you're defined to be what it looks like you ought to be. If you hadn't noticed that there was a problem there, you would have still gotten the right answer. But I suppose situations could come up where if you weren't careful, something bad might be happening. Like, instead of there being a natural value at t equals 0, it might be going to infinity or something weird. Anyway, moral of the story is, if you're doing an integral and you're working with a function that has a branch cut, you got to watch out for that branch cut. You got to think carefully about what's going on there. Next, we need to establish a theorem that we're going to need to prove an even bigger theorem a little later. So we'll start with proving a lemma that gives us a bound on these kinds of integrals where you have a sort of parametrized curve inside the integrand there. which we know that we evaluate just by breaking it into its real and imaginary components or finding an antiderivative. These kind of integrals that are appearing here in this lemma, those are the kind of integrals you get after, when you have a contour integral and then you substitute in your parameterization for your contour, it ends up turning into one of these kind of integrals. And so the lemma here says that if your w of t is a piecewise continuous complex valued function, such as you would get when you're looking at a contour, defined on an interval a to b, then the modulus of this integral from a to b of w of t dt, this works out to be less than or equal to the integral from a to b of the modulus of w of t. So let's look at a proof of this. So the first thing, we need to rule out the possibility that integral is equal to 0. Let's just point out that if the integral from a to b of w of t dt happens to equal 0, well then clearly this thing is true, because the integral on the right hand side is integrating. It's a real valued integral, right? Because you're taking the integral of a modulus, which is just a it's a real function. So if you're integrating a non-negative function, you always get a non-negative value. So if the integral on the left over there is 0, then clearly the result is true. So let's suppose that integral is not 0. So when you do the integral inside the modulus on the left, you get some complex number, and it's not equal to 0 at this point. So let's suppose the integral from a to b of w of t dt equals r naught e to the I theta naught, where r naught's not equal to 0. So you can do a little bit of a clever thing here. We could solve for r naught in this previous equation. So r naught, we could write that as, just divide both sides by e to the I theta naught and move it inside the integral, and you'd get r naught equals the integral from a to b of e to the negative I theta naught times w of t dt. So the thing to note here is that r naught is a real number because it's the radius of the complex number. In fact, it's a non-negative real number, but right now what really matters is that it's real. So we could say r naught, you have to remember the way that we compute the integrals that r naught is equal to is you break it into a real and imaginary part, and then you integrate the real part and the imaginary part separately. But since that integral works out to be a real number, that means that the integral of the complex part is 0. So you can say that r naught is equal to the real part of this integral, which by the way that we compute those integrals is really just integrating the real part of the integrand. And now we can look at that integrand that defines r naught. Now you may remember we pointed out an inequality a long time ago when we were talking about moduluses. There's an inequality that says that the real part of z is less than or equal to the modulus of z. It's kind of simple. It's just because the modulus of z is equal to x squared plus y squared, and that's on the real part of z is just x, right? So x is certainly less than or equal to the square root of x squared plus y squared. So we're going to use that and say this is less than or equal to the modulus of e to the negative I theta naught w of t, which we know from properties of modulus that we can break that into the modulus of the first term of that product times the modulus of the second term in the product. And that e to the negative I theta bit has a modulus of 1, so this is just modulus of w of t. So that tells me, if I go back to looking at r naught, which is equal to this integral from a to b of the real part of e to the negative I theta naught w of t dt is less than or equal to the integral from a to b of the modulus of w of t. But remember, r naught is the integral in question, right? I guess let's make that a little bit more transparent. If we take the modulus of the original integral, remember we said that integral up here, we said that integral was r naught e to the I theta naught. So at the bottom here, the modulus of that whole integral is really the same thing as the modulus of r naught e to the I theta naught, and clearly that modulus is just r naught. So that tells me that modulus of from a to b, the modulus of the integral from a to b of w of t dt is less than or equal to integral from a to b of modulus of w to t dt, because this thing over here is just r naught, and we already established that r naught was less than that quantity on the right. So there you go. So this lemma was needed to establish the next theorem, which is what we're really interested in. So let's see what that one is. So here's the theorem that we really want to consider, because we're interested in doing contour integrals. So let C be a contour with a length of L, and we suppose that our function that we're integrating is piecewise continuous on that curve. And we're also going to suppose that our function has a bounded modulus along that curve, everywhere where it's defined on that curve. So we could have the situation where the function has a branch cut and the contour crosses that branch cut a finite number of times. But in any event, if you have the bounded function on the curve, then it turns out that the modulus of the integral over the contour C of f of z dz would be less than or equal to that upper bound on the modulus of the function multiplied times the length of the curve. All right, so let's see how we might prove this. Well, if we want to sort of get our hands on the integral, we need to have a parameterization for our contour. So let's start with that. So let's let z of t be a parameterization of c, and we've got to have some interval for t here. Let's say t goes from a to b, and then of course we'll suppose modulus of f of z is less than or equal to m for every z that's on our contour where the function is defined. Of course, we're assuming here m is bigger than or equal to 0. The integral over c of f of z dz, just by definition of contour integral, would be integral from a to b f of z of t times z prime of t dt. And so then if we take the modulus of that, by our previous lemma, we can say that that integral is less than or equal, I can pull the modulus in basically. So this would be integral a to b modulus f of z of t times z prime of t dt. And now we're dealing with a real valued integral, because we're taking the modulus of the stuff that you're integrating. So, we can use stuff that we know about real valued integrals. Well, this integral here, I can break up that modulus into a product. And this f of z of t, we know by hypothesis, we know f of z is less than or equal to m for any point on that curve. And so z of t is a point on the curve. So we know that this is less than or equal to integral a to b of m times modulus of z prime of t. And of course you can pull the m out. And then the expression that you're looking at here is exactly the length. This integral is exactly the length of the curve. So this is m times l, which establishes the theorem. Now there is one little caveat here, because in the statement of the theorem, we were supposing the function f of z was piecewise continuous on this curve, and that we were allowing for some finite number of places where the function is undefined on that curve. But all that just means is that you'd have to break up this integral into a finite number of integrals, and the problems would be at the endpoints, and you could easily fix up those integrals at the endpoints, kind of like we did with the branch cut stuff in the previous example. It's at this point right here, we only have that inequality where the curve is defined, but at those places where the curve is not defined, we just break it up into several integrals, and then it would still be true. You just have to break it up into a sum. So rather than having to spell all that out, we'll just leave it at this. And let's do an example that shows how you could make use of this previous theorem. So it just gives you a way to get some upper bound on some integrals. So in this particular example, we've got this integral z minus 2 over z to the fourth plus 1 dz. This isn't the sort of thing that you're going to easily find an antiderivative. I mean, we could certainly try to take the parameterization of the curve and substitute it in, and but I think we'll end up with an integral that's fairly yucky, and we might not be able to work it out. So the previous theorem just gives us a way to get a handle on how big that integral would be in modulus, which might be useful in certain situations. You don't have to actually compute the integral though to get this upper bound. Is the cool thing about it. I don't even really have to work with the specific parameterization of that circle to make this theorem work. That previous theorem tells me if I can find an upper bound on the function being integrated, then I can use that to get an upper bound on this integral here, because I can certainly calculate the length of that arc. So let's look at the modulus of z minus 2 over z to the fourth plus 1. Well, according to the Pythagorean identity, this would be less than or equal to, first let's say we're doing z minus 2 modulus over modulus z to the fourth plus 1, just using the property of modulus there. And the numerator, we know, using the Pythagorean identity, would be less than or equal to modulus of z plus modulus of negative 2. And then we could make the denominator smaller by using sort of that reverse triangle inequality. We could say the denominator gets smaller by replacing it with modulus of modulus, or absolute value of modulus of z to the fourth minus modulus of 1, like that. So this last inequality here is just due to the triangle inequality, because we've made the denominator smaller, which makes the fraction bigger. Now you can see along the curve, if you just focus your attention to the values of z on the curve C, we see those points all have a modulus of 2 because we're on the semicircle here. So then along C we have modulus of the original function we're integrating. So less than or equal to the modulus of z plus modulus of negative 2 over absolute value of modulus z to the fourth minus modulus of 1. So this works out to 2 plus 2 over absolute value of 2 to the fourth. So that'd be 16 minus 1. So you end up with 16 minus 1. So 4 over 15. So we know that the function we're integrating in modulus is less than or equal to 4 over 15 along that curve, okay? Because this was a semicircle or quarter circle, and the points all along that have modulus 2. All right, so then now we can apply the previous theorem. The modulus of the integral along C of z minus 2 over z to the fourth plus 1 dz is less than or equal to this upper bound that we established, 4 over 15, times the length of that radius 2 quarter circle. So that'd be 1/4 of 2 pi r, and the radius is 2 here. So that just equals 4 pi over 15. So there we have an upper bound on that integral that we got without having to do any integration whatsoever. This sort of thing is pretty handy a little later. Turns out that you can use complex integrals to get a handle on what certain real valued integrals are doing if you work around circles. Sort of you go around problem places. It's hard to make what I'm saying very precise right now, but just being able to get an upper bound on an integral going around some circle in terms of the radius of that circle gives you a way to sort of take limits and get rid of things. So anyway, this sort of process will be handy later. Okay, here's another example. We're going to show that if we got a semicircle, we're going to call C sub r, that is just the top half of the circle centered at the origin of radius big R. And we're going to show that if we take the contour integral of this fraction in the example below around that curve with this variable radius, and then we take the limit as the radius goes to infinity, that those integrals shrink to nothing. So we can do this pretty similarly to how we handled the last problem. You first look at the function that you want to integrate, and if you want to look at the modulus of it, we could say that that's the modulus of the top over the modulus of the bottom, and when you take the modulus of the denominator, you can break that into a product of moduli, and then you can use the triangle inequality in the numerator and get a fraction that's bigger than the previous one. And then we can do the reverse triangle inequality and get something that's smaller in the denominator, which makes the overall fraction bigger. So if we do the reverse triangle inequality in the denominator, we get the absolute value of modulus of z squared plus modulus of 4, which is 4, times absolute value of modulus z squared plus modulus of 9, which is 9. So we have this, and so then we could point out, well, then along C sub r, which is this semicircle centered at the origin of radius r, where all the points have modulus r. So the modulus of our function that we started with there, along that arc, would be less than or equal to r plus 1 over r squared plus 4 times r squared plus 9. So then we can say that this integral along c sub r, when we take the modulus of it, is less than or equal to this expression that we just got, times the length of our curve. Now our curve is just this semicircle of radius r centered at the origin. So it's just half of 2 pi r, right? So it'd be pi r. And that's the length of the arc there. And so you can see that in this expression, it's a rational expression in terms of r, where the degree of the numerator is 2 and the degree of the denominator is 4. So clearly it's going to go to 0 if you take the limit. So the limit as r goes to infinity, the modulus of this integral. I guess it bears pointing out that, of course, we're sort of doing the squeeze law, right? It's like that integral that the modulus of that integral that we're looking at, certainly it's bigger than 0 because you're taking moduli. So it's bounded between two expressions that as r goes to infinity, both go to 0. So we end up with the limit of that expression is equal to 0. Just a simple application of the squeeze law there. I think this particular example actually comes up again a little later in doing a specific kind of integral that has to do with residues, but we'll get there. The main point now, though, is to understand that we can get bounds on integrals sometimes without actually having to do any integration. We get the bounds on the integral simply by getting a bound on the function that you're integrating and then knowing the length of the curve that you're integrating along, which makes life kind of easy sometimes. All right, I think I'm going to stop right there. We'll have one more technical theorem about when we can use antiderivatives and have independence of path. And then we're going to be getting to a really cool, the really cool theorems about how to do contour integrals. We're almost there, past the technical stuff. All right, talk to you again soon. Bye.